The broadcast is now starting. All attendees are in listen-only mode.
Good day, everyone. Welcome to our webinar entitled Why HRG is Considered an Arc Flash Mitigation Technique by NFPA 70E and CSA Z462. My name is Sergio Panetta from I-Gard Corporation. And before we start, I just want to wish everyone well wishes and make sure you're all staying very safe in this period of flux. All right, so we're going to discuss a couple of standards that's important. Z462 and its counterpart in the United States, 70E, although, yes, 70E. CSA C22.1, which is the Canadian Electrical Code, and NFPA 70, which is the National Electrical Code. Of course, with these standards come other standards that are being used, ANSI Z10, as well as CSA Z1002, I believe, which is the safety management systems. That's often used, and you can see the triangle here for the hierarchy of controls in 70E. It's very important. So in the Annex O of Z462 and NFPA 70E, 0.2.3, design option decisions should facilitate the ability to eliminate hazards or reduce risk by doing the following: reducing the likelihood of exposure, reducing the magnitude or severity of exposure, enabling achievement of an electrically safe work condition. .2.3 of CSA Z462 and NFPA 70E has some incident energy reduction techniques. So we're going to discuss all of these, and then we're going to focus a little bit on why HRG is considered an arc flash mitigation technique and what the difference is between all of them. Obviously, we have zone-selective interlocking, differential relaying, energy reducing maintenance switch. There's also a caveat there with local indication, energy reducing active arc flash mitigation system, arc flash relay, HRG, current limiting fuses, and a shunt trip. The National Electrical Code also goes a little bit further in clause 240.87, breakers with adjustable trips greater than 1200 amp, methods of reducing clearing time. So we're trying to reduce the clearing time. Zone-selective interlocking, differential relaying, energy reducing maintenance switch, and now it says energy reducing active arc flash mitigation system, instantaneous trip, which is less than available fault current, instantaneous override, less than available fault current, or an approved equivalent method. So before we start into why we're trying to reduce the incident energy, we have to do a incident energy study, and for that we use IEEE standard 1584, which is the IEEE guide for performing arc flash hazard calculations. The formulas are horrendous, I'm sure, if you had to follow. I'm glad I never had to solve these ones when I was in school. But the energy on 600 volts is this constant times T. T is in milliseconds here. Some of the other formulas, or some of the other constants we have here are blown fault, or voltage fault current. G is gap, D is distance, and a correction factor. So there's equation for 600 volt, 2700 volt, 14.3, and less than 600 volt. So we could see that the incident energy is directly proportional to time. So we have to note that the faster we can isolate the circuit, the faulted circuit, the lower will our incident incident energy E. So zone-selective interlocking was the first method discussed. This is a method that allows two or more circuit breakers to communicate with each other so that the short circuit or ground fault will be cleared by the breaker closest to the fault. We've all done propagation studies, and a properly coordinated system always has the fault closest, the protective device closest to the fault isolate. Unfortunately, what happens is when we have nested protective devices, we intentionally put in time delays on the main breaker or feeder breakers because we definitely want those to trip last in an event when we have an arc flash. So if we have a fault that occurs here, there's an intentional time delay in this feeder breaker because we want this breaker to open first if there's a fault here. So we put in a time delay here and then an additional time delay on the main breaker. And so our fault curve, our protection curve looks like this. When, however, you have a fault on the system and you turn on the zone selective interlocking, the time delay is removed from the circuit. And when the time delay is removed from the circuit, we can trip much faster because there is no intentional time delay. So we reduce the amount of time it takes to clear that fault. Incident energy is directly proportional to time. So when you reduce the time, you reduce the incident energy. So out of our reduced zone selective interlocking, reducing the likelihood of exposure, reducing the magnitude or severity of exposure, enabling achieving an electrically safe work condition. It reduces the magnitude or severity of exposure because you need to have an arc flash first, and it reduces the time that the fault is on the system, thereby reducing incident energy. Differential relaying is another technique used to reduce incident energy. This concept of the protection method is the current flowing into a protected equipment must equal the current exiting that equipment. If these two currents are not equal, a fault must exist within the equipment. Differential relaying uses current transformer located on the line and load side of the protected equipment and fast-acting relay. So the current going into this piece of switchgear must equal the current exiting the switchgear. This is a single line diagram, so there are three-phase PT, so you can see that we sum the currents entering and the currents exiting are subtracted from that, and if the current equals 0, there's no fault within the system. If you have a fault outside of this zone, the current going in equals the current going out, so there's no fault within the equipment. When you have a fault inside that piece of equipment, then the current coming in does not equal the current going out. Therefore, it's easy to detect non-zero current, and so we can trip much faster. And we can probably trip this in 100 milliseconds. The zone of protection for this is obviously between the breakers coming in and the breakers going out. So we're only looking at a specific area that we're trying to protect. This technique reduces the magnitude or severity of exposure. It doesn't reduce the likelihood of exposure. Energy reducing maintenance switch. The energy reducing maintenance switch allows a worker to set a circuit breaker trip unit to operate faster while the worker is working within an arc flash boundary as defined in NFPA 70E for 70E in clause 3 in Z462, and then set the breaker back to the normal setting after the work is complete. I'm sure you've all seen these things. It's a maintenance switch. There's usually a blue light that goes along with the maintenance switch. You turn it on. So what we're doing is we're sacrificing coordination in order for personal protection. We lower the instantaneous setting of that breaker to a current which is less than the arcing current, so we trip much faster. So when we have a fault, if a fault does occur, the feeder breaker will trip immediately because the threshold of the instantaneous is greatly reduced, and we can pick that up faster. Again, we sacrifice coordination when this happens, but we sacrifice coordination in order to have personnel protection. This as well reduces the magnitude or severity of exposure. It doesn't reduce the likelihood of exposure. These techniques only look after the fault, take care of the fault after the fault occurs. Energy reducing active arc flash mitigation system is another technique that's used recommended by NFPA 70E and Z462. This system can reduce the arc duration by creating a low impedance current path located within a controlled compartment to cause the arcing fault to transfer to a new current path while the upstream breaker clears the current. The system works without compromising existing selective coordination in the electrical system. This system as well reduces the magnitude or severity of exposure. And we're going to go through a tech. So what happens here is we basically have a crowbar. We create a three-phase short circuit to ground, eliminating the voltage. When there's an arc flash detected by these arc flash sensors, so we simultaneously close this contact between phases and ground and open the main breaker. The main breaker takes 83 milliseconds to operate and completely open. So of all the techniques we've had, not one of them was below 5 cycles in time to clear the fault. This fault, however, can clear a fault very quickly. Imagine if you have this is your three-phase short circuit to ground. So we're going to connect all three phases to ground, and all manufacturers have this. At t equals 0, you have a fault. At t equals 1 millisecond, you've detected that light sensor, because light is an easy thing to detect inside a piece of equipment. So when we detect the fault in 3 milliseconds, we simultaneously close this switch and open the circuit breaker. We issue a command to close the switch, and we issue a command to open the circuit breaker, which is feeding this faulted area in 3 milliseconds. Between 4 and 5 milliseconds, we've created a three-phase short circuit to ground, thereby eliminating the voltage. But what we've done is we've swapped a arcing fault into a three-phase bolted fault. We still have to wait a full 83 milliseconds for that circuit breaker to open the fault. However, there is no potential because everything has shorted to ground, so there's no potential difference and thereby less incident energy. Again, you're trading one fault, which is an arcing fault, to a three-phase bolted fault. You still have to go in, maintain the gear after that, make sure that your circuit breakers still work, your transformer is okay. It may take some time to bring the system back up, but you've ensured safety to the personnel who are operating on this gear, because you've eliminated that fault in 4 to 5 milliseconds. With rough calculations, you can actually be below the 1.2 calories per centimeter squared defined in 70E and Z462 by using this method, because you're not waiting for the circuit breaker to open in 83 milliseconds. You can clear that fault in 4 to 5 milliseconds. And sometimes you can do this. However, you're trading one fault, which is an arc beam fault, into a three-phase volted short circuit. And that's why they say it's a low impedance path. In fact, some standards in Europe specify that the impedance of this fault cannot be greater, in this short circuit, cannot be greater than a certain ohmic value. This, again, reduces the magnitude or severity of exposure and only protects you after the fault has occurred. Arc flash relay. An arc flash relay typically uses light sensors to detect the light produced by an arc flash event. Once a certain level of light is detected, the relay will issue a trip signal to an upstream overcurrent device. In this example, we have light sensors within the gear, and when the light sensor is detected, we open up the circuit breaker, or the overcurrent device, which is protecting this section. And again, the 1 millisecond possibly to detect the presence of light, and 83 milliseconds to open and clear that fault. We've reduced the time that the fault is in the current. It's easier to detect light than to detect overcurrent. But you may want to use this technique with a overcurrent device and ensure that there is truly a fault in the system, or a light and a pressure technique to determine that there is truly a fault in the system. Many manufacturers have different techniques that they use. Sometimes they use light and current. Sometimes you can use light only. Sometimes light and pressure. Some light and sound. There are different techniques you can use, but they all basically start with the same thing. Detect the fault as quickly as possible, clear the fault, reducing the time that the fault is on the system. Our zone of protection is from the load side of the main breaker on. But we're only protecting this cell. If you had an arc flash in this area over here, you would not see it here. And therefore, we're only protecting a certain area of the facility. This technique also reduces the magnitude or severity of exposure. It does not reduce the likelihood of exposure or enable achieving an electrical safe work condition. Current limiting devices. Protected devices reduce incident energy by clearing the fault faster and by reducing the current seen by the arc source. The energy reduction becomes effective for current above the current limiting threshold of the current limiting fuse or current limiting circuit breaker. So what happens here is we have an arc flash, and the current produced by the arc flash will, if it's greater than the current limiting limit of this fuse, will open this fuse very quickly. A fuse can open faster than a circuit breaker. So this is why you can use fuses in the current limiting range to be an arc flash mitigation technique, because you will decrease the time that the fault is on the system. So we're only looking at the load side of the fuses and down. That's a zone of protection. This technique will reduce the magnitude or severity of exposure. It will not enable and achieve an electrical safe work condition, or nor reduce the likelihood of exposure. In combination with the current limiting fuse, we can add a shunt trip that's signal to open from an open fuse relay. So if your relay in the current limiting range opens, the first fuse to open triggers a relay to clear the fault from the upstream breaker to open up. In this condition, we clear the time that we decrease the time that the fault is on the system. So basically, if we have a fault down here, when the first fuse on this three-phase fuses opens up, we send the signal to this blown fuse relay and open this contactor with a shunt trip. And this reduces the time that the fault is on the system. We've increased our zone of protection to the line side of the breaker now instead of, the load side of the breaker now instead of the load side of the fuse, as shown in the current limiting fuse range. The shunt trip will reduce the magnitude or severity of exposure. It doesn't reduce the likelihood of exposure. For IEEE color books, arcing faults, a disadvantage of solidly grounded systems involves the high magnitude of destructive arcing ground fault currents that can occur. Solidly grounded system has the highest probability of escalating into a phase-to-phase or three-phase fault, particularly for 480 and 600 volt systems. The danger of sustaining arcs for phase-to-ground fault is also high for 480 and 600 volt systems and low for or near zero for 208 volt systems. So we've known that three-phase faults can occur from ground faults. High impedance grounded systems, a great majority of electrical faults are of the phase-to-ground type. There's literature out there, which I'll explain to you later, says that perhaps 95 to 98% of all faults begin as single phase-to-ground faults. By utilizing a high resistance grounding system, an impedance is inserted between the neutral point of your power source and ground, typically limit the fault current to 10 amps and below at 5 kV or below, leaving insufficient fault energy and thereby helping reduce the arc flash hazard level. High resistance grounding will not affect arc flash energies for line to line or line to line to line arcs. So basically what happens here is you have a fault, ground fault. Ground faults, if not cleared in a certain time period, will propagate to phase-to-phase or three-phase faults. If you have a high resistance grounding system, and I apologize, there should have been a resistor over here, by limiting that current to a low value, 10 amps or less, on systems 5 kV and below, this is considered an arc flash mitigation technique. So one resistor on a 480 volt or 600 volt system, let's say we have a 600 volt system, by placing a 69 ohm resistor, approximately 1800 watts, protects the entire system and gives you credit for an arc flash mitigation technique. This system reduces the likelihood of exposure. It doesn't reduce the magnitude or severity of exposure. NFPA 70E and Z462 says high resistance grounding will not affect arc flash energy for line to line or line to line to line faults. By placing a resistor in the circuit does not affect the bolted fault current if you have a three-phase short, thereby not reducing the incident energy by using high resistance grounding. Famous book by Dunkey Jacobs says that 95% of all electrical faults are phase-to-ground faults. They propagate to phase-to-phase or three-phase fault. By limiting the fault current to a low value, 10 amps or less, there is insufficient current for the arc to restrike and it self-extinguishes. And this book is available online. Excellent book. One of my colleagues did a test on a 13.8 kV system, resistance grounded, and they reduced the current to a 50 amp arcing fault. So what they did is they had a 400 kc mil aluminum conductor with a number 6 copper wire, and they created a fault with this 50 amp ground fault current. It was a ground fault produced by a 6-gauge wire. So a lineman pushed this number 6 wire towards the aluminum conductor and until an arc started. The arc restarted twice and arced continuously for 128 seconds. 14 inches of the copper wire was melted. When that current was reduced to 18 amps of arcing, the resistor was changed. The intermittent arc, it was arcing for 208 seconds, and after numerous tests, arc would not sustain itself. So the lower the current, the less energy to sustain the arc. This is at 13.8 kV, and going from 50 amps to 18 amps, it was difficult for that arc to sustain itself. So you can imagine at 10 amps, you would have less energy and less damage. But that's not the only benefit you get from the high resistance grounding system. In this particular graph, we had one customer who changed an entire facility from a solidly grounded system to a resistance grounded system simply for an arc flash mitigation technique. Even though when they did this, they did not lower incident energy, they felt that having a high resistance grounded system in their facility would give them an arc flash mitigation technique that they wanted. What they found after producing this or changing these their transformers from solidly grounded to resistance grounded is that their motor repair cost decreased tremendously after all the substations were changed. They saved so much money on the motor repair costs that the money they saved in not replacing or repairing motors more than paid for the capital to change the facility to high resistance grounding. In CSA, the Canadian Electrical Code, you can increase productivity because you don't have to trip if your fault is limited to systems 5 kV and below, and if you limit the fault current to 10 amps or less. 10-300 through 10-308. So you have an arc flash mitigation technique. You save money because you're not having as much damage or destructive damage at the point of the fault. And you can continue working when you have a ground fault. The NEC says the same thing. If you have a high impedance grounded neutral system, you limit the fault current on systems at 480 volts to 1000 volts, the conditions of maintenance and supervision ensure that only qualified persons service the installation, ground detectors are installed, and line to neutral loads are not served. So you have a arc flash mitigation technique. You save money because you basically you have less damage at the point of the fault, so there's less destructive current. You can continue operation, and now you can help you find where the fault is with pulsing. In a pulsing system, if you vary the resistor here by using this contactor, you can vary that resistance, and when you vary that resistance, you change the fault signature in the faulted path so you can find where the fault current is or where the fault is in a very short time. We've had some people say that they want to have solidly grounded systems because if they have a ground fault, they want something to happen. But why do you want something to happen if you can actually find the fault in a high impedance grounded system in a short time? So when you have a fault, you start the pulsing, and the fault circuit only exists in the faulted path. So our faulted path is anywhere in that path, we will see the pulsing signature and thereby find where that fault is. And we can find that fault with a high impedance grounded system in any size facility in less than 1 hour. With this system, we have pulsing here. We can find the fault even without opening up any cells. And we do that with our technique of, if you look at the, please try to pay attention to the bar graph over here. Try not to look at the numbers because you'll drive yourself nuts if you look at those numbers. So we've got this CT around conduit, and we can detect that signature of the pulsing around conduit, so you don't have to open up cable trays or cableways to look for where the fault is. So to summarize, we have an arc flash mitigation technique. You have less damage at the point of the fault. You can continue operation, and you can find where the fault is without putting people in harm's way with a high impedance grounded system. It's the only protective system, arc flash mitigation system, which helps you before the fault occurs. Everything else reduces the severity or the magnitude by reducing the time it takes to actually clear the fault. High resistance grounding is the only technique which prevents the fault from the three-phase fault occurring in the first place. You're still going to get the incident energy associated with the three-phase fault. The maximum fault energy is there. We don't lower the incident energy by playing with high resistance grounding, but you end up with a much safer system. In this example, we have a arcing three-phase fault on a high resistance grounded system and an arcing three-phase fault on a solidly grounded system. There's less damage when you have a high resistance grounded system. Oh, that's more now. Any questions?
Hi, Sergio. Yes, so we did receive some questions. Okay, so one question we received is, when there's not a maintenance switch available on a circuit breaker, is it acceptable to adjust the instantaneous dial to a lower setting to perform the same mitigation?
The problem with that technique is that when you finish doing the maintenance, what happens if you forget to put the instantaneous back to where it was? It's better to have a maintenance. I mean, in the absence of a maintenance switch, I guess yes, you can do that, but it's not really good because you may not put it back to where it was before, and you're changing the settings. I guess you're changing the instantaneous pickup, and you may not put it back in the right place when you start it. So it performs the same function, but I don't believe it's the same technique as the maintenance switch defined by NFPA 70E and Z462. Because if you look at the wording of NFPA 70E and Z462, it says a maintenance switch with local indication. So if you don't have that local indication, I don't think they would consider that a mitigation technique. You have lowered the incident energy, but you can't consider that a technique. I hope we're going to answer all these questions, even the ones that I answer here, because to make them coherent.
Thanks, Sergio. Yeah, so we'll release an entire question and answer document next Tuesday, but we will still address some of the questions right now. We did get quite a few. The next one is, can you comment on HRG applied in data centers?
I think in data centers, HRG and data centers work very well in data. Sorry, high resistance grounding is an effective tool to use in data centers because data centers should not be isolated in case of ground faults. Remember, we said, Duncan Jacobs said that 95% of all faults begin as single phase to ground faults, and they propagate to a three-phase fault. If you have a solidly grounded system in the data center and your fault, if you have a 90% probability of having a ground fault, you're going to trip something. In data centers, you do not want to trip. In Canada, we put high resistance grounding systems in hospitals as well as data centers. So it is a better technique to use a high resistance grounded system in a data center and hospital because you do not want things to trip, specifically in hospitals and data centers. The other thing is, a lot of data centers have generators and transformers, or transformers and a generator as backup. With our HRG system, you can have one HRG system which is transferred to either the generator as a source or the transformer as a source. You can have one HRG system with two resistors, one on the generator and one on the transformer, and you end up with a safer system because you don't need to look at the HRG system to the generator and the HRG system at the transformer as two separate HRG systems. You can have one HRG system controlling two different resistors and have a safer system because the operator is always looking at the same HRG system to indicate whether there's a fault on the system. The only thing you have to watch out for when you have HRG systems on data centers is the type of UPS you're using. Make sure the loads are compatible with the HRG system, period.
Great, thank you, Sergio. And regarding data centers, we also do have an installation reference guide online, and data centers are an industry in which we work with frequently. So if you want to take a look at that document, it might help you out with what products and where we've installed previously. Next question. Can you describe what happens with double ground faults on HRG?
Okay. If you have, well, sorry. Sorry, just get into a double ground faults. Okay, so basically what happens when you have a double ground fault on a HRG. So basically, if you have, let's look at the double ground fault. If you have a fault on the same phase, two phase to ground faults, then you will look for one, clear it with the pulsing, and then find the other one and then clear that one. If you have a fault on two different phases, so let's take a look at this. If you have a fault, well, we'll put the first fault back on. That first fault is on B phase. Let's say you develop another fault on one of the other unfaulted phases. So let's say you have a fault on C phase on this breaker. Now you have a phase to ground to phase fault. A lot of HRG systems out there will not be able to detect this. We have a specific HRG system that looks specifically at this type of a fault. And so for data centers, hospitals, or any industrial facility, our system, we have a system which will detect the presence of this double fault and clear the feeder, which is declared the lower priority. And when that happens, we can maintain your critical load operating at all times, because the feeder, which you have defined as less important, will open first. And we can typically open before the instantaneous of the protective device. That's what happens in a double fault. The resistor is not even in the circuit in a double fault. So that's why a lot of manufacturers of HRG systems cannot distinguish this type of fault from a normal single phase to ground fault.
Thank you. Okay, next question. If the NGR is open, can the sensing resistor still detect ground fault and trigger a ground fault alarm?
It depends on how you're detecting the ground fault.
Okay.
Well, no, I'm not finished yet.
Okay.
A lot of the manufacturers of HRG system are going to put a CT on the resistor to detect the ground fault. And when a fault occurs, you're going to get this ground fault path, and you're going to detect that current. If your resistor is open circuited, you're not going to get that fault current, and thereby you have an ungrounded system, which is very dangerous. We have several systems where we can actually monitor the voltage on the bus and calculate or determine if there's a fault on the system, and then combine that with the current going through the system to determine what feeder the fault is on, what phase the fault is on, and if the resistor is open, we can still indicate the presence of a fault, because when you have an ungrounded system, well, this is very poor, but the two unfaulted phases elevate to line potential with respect to ground. So we would be able to detect that as a bus fault. We're not measuring the corresponding current, but we do measure the voltage, and thereby we can detect that even if the resistor is open. However, if you're in Canada, if you have an open resistor, you have to trip right away in a high resistance grounded system.
Okay.
Now I'm finished.
Great. One slide mentioned that HRG cannot be used on a system where the neutral is used to serve a load. Does this mean that this cannot be used on a 480 277 volt systems if there are 277 volt loads?
Okay, now that's a tricky question, because in the United States, according to the NEC, you cannot use a high resistance grounded system on a distributed neutral. However, if you have single phase 277 volt loads, what we can do is have a 3-phase high resistance grounded system and put an isolation transformer here and service your lighting loads at this location, and have a separate lighting panel and lighting loads, and end up with a safer system, because now your electricians, when they're changing these ballasts, are exposed to much less incident energy by this transformer than this transformer. In Canada, it is possible to have a high resistance grounded system with a distributed neutral. However, you must trip at the very first fault. And there are some other implications in Canada as well. But in the United States, You cannot have a distributed neutral. In Canada, you are allowed to have a distributed neutral.
Okay, thank you. One person is wondering how to size or select HRG for their system.
A high resistance grounding system must, the current which you limit the fault current to in a high resistance grounding system must be equal to or greater than the capacitive charging current of your system. If you need some information, what we can do is when we answer these questions, we can post our application guide on how to calculate or how to measure capacitive charging current on your system. But an effective high resistance grounded system will have the resistive current greater than the capacitive current. So you have to calculate what your resistive or what your capacitive current is before you can implement your resistive current.
Okay. Next question. The implication of HRG is in, sorry, here I lost my place. The implication of HRG is in elevation on healthy phases. What kind of voltage protection should be used?
In 600 and 480 volt systems, or even 5 kV systems, if you put lightning arresters on 5 kV systems, they must be rated full phase to phase with respect to ground. So you have to have surge protective devices or lightning protection, which is greater than the phase to phase voltage with respect to ground. So manufacturers of surge protective devices in low voltage systems will have a specific part number they use for high resistance grounded systems. And what they'll do is, if you look at the nameplate of the surge protective devices, they will have the line to line protection voltage equal to the line to ground protection voltage.
Okay.
One more thing that we wanted to add in a high resistance grounded system. Although we don't get credit for reducing incident energy in a resistive grounding system, we've had several of our customers tell us that they would employ a high resistance grounding system and spend the money on a high resistance grounding system as an arc flash mitigation technique if you can lower the incident energy as well. And we have a module, because we manufacture the ground fault protection relays and the resistors and the high resistance grounding system. We've developed an optical sensor which can be used in conjunction with our high resistance grounding system, which will trip the breaker faster, and thereby you get the technique of reducing the likelihood of exposure, and then the arc flash relay of reducing the magnitude or severity of exposure. Now you get the best of both worlds, because you have protection of 95% of the faults because of the high resistance grounded system, and the other 5% of the faults by having the arc flash relay that happens within that area.
Okay.
And we can send out literature to that effect as well.
Great, thank you. Moving on to the next question. Is there an option to add arc mitigation to HRG in effort to reduce magnitude and probability?
Jessica?
Yes.
That was the question I just answered.
Oh, oops.
But yes, we have the ability to add an arc flash module to our DSP Omni relay and have the reducing the likelihood of exposure with the resistance grounded system, and to reduce the magnitude or severity of exposure So with our combined arc flash relay and high resistance grounding system, we can check both of these marks off.
Okay. Next question. Once the fault occurs, what is the maximum time in which the fault should be cleared?
That's a tricky question. When you have a high resistance grounding system, I've seen faults on systems that lasted greater than 6 months because there are people that don't know how to find the faults. But it's up to the operating method or procedures of the particular facilities to determine how much time the fault is on the system for. We've had some customers in pharmaceutical that say things like they have job techniques of if a ground fault exists on a high resistance grounding system, they will allow their operators 8 hours, or the electricians 8 hours, to clear that fault. Otherwise, they're going to trip the circuit breaker. So we have ground fault protection, high resistance grounding system with feeder protection. We can actually program the feeder protection to trip on the first fault instantaneously, to trip on the first fault with a time delay, or trip on the second fault only. So if you program the relay to trip on the first fault with a time delay, you can have an 8-hour time delay or a 99-hour time delay and allow the electricians enough time to look for the fault. But if they don't find the faulted feeder will trip.
Okay. Next question. Does pulsing not require relays for each feeder load?
No, it doesn't. With pulsing, the only thing you need to have with pulsing is a contactor that changes the resistance value here. Sorry. We can change the resistance value here. You don't have to have a separate relay. We have relays or a system which will measure this current here and here and here and determine which feeder the fault is on. This gives you the second fault protection. However, for pulsing only, all you really need is the contactor here and a resistor, and we change the fault signature. But with our DSP relay, we can actually tell you, most manufacturers of high resistance grounding systems are going to say, you have a fault somewhere. With our system, you can say, you have a fault and it's in feeder number 2. Well, in this case, feeder number 3.
Okay, great.
So,
I think we have time for one more question. We are approaching the 3 o'clock mark. So we'll do the last question now. And as we said, there will be the Q&A document released next week, and all the questions will be answered there. So for the final question today, is HRG compatible with VFD's applications? Is there anything specific to watch out for?
We had this question 2 weeks ago. It depends on the variable frequency drive. Most variable frequency drives are compatible or can be made compatible to high resistance grounding systems. There's no problem when a drive is compatible. There are issues with some drives that are not compatible. For example, any slash rated devices, and slash rated devices are 480, 277, so they don't have the isolation to ground in case of a ground fault. So those types of devices are not compatible with resistance grounding systems, and that's what happens sometimes with some brands of variable frequency drives. But typically, if a drive can be made compatible with the resistance grounding system, there is no issue.
Great, thank you. All right, so that was our last question, but feel free to continue submitting your questions for the next couple minutes because we will address them in the document being released a week today. We did have a few questions about the webinar recording. Yes, it is being recorded and it will be available on our website under the webinar tab. The audio and visual will be there so you can watch it on demand. And then be sure to visit our LinkedIn page as there is an invitation outlining all of our upcoming webinars, dates, times, topics, with registration links there for you. Sergio, anything else from you?
No, just everyone, please be safe out there. Everybody has to do their part. But most importantly, please be safe.
Perfect, thank you. Thanks for attending, everyone. Please feel free to email jcraig@i-gard.com if you have any other requests, comments, questions, anything like that. Alrighty, thank you and have a good rest of your afternoon. Bye-bye.